So hi, everyone. I'm Shane. I'm a lecturer in the computer science department, but I have more of a hardware engineering background. Sorry, click it there. So the data center infrastructure is evolving. And the way that it's changing is that it's starting to fill up with smart things, which might sound kind of like a strange thing to say. Data centers are surely full of smart things. They're full of computers. But what I mean here is that there's a new kind of naming convention coming out for a type of computing device that's starting to take over the data center infrastructure. In particular, smart NICs, and a NIC is a network interface controller, and smart SSDs. So SSDs are solid state drives or hard drives. And by talking about them becoming smart, what we mean is we're adding more compute capability to them. So we're putting big kind of processing types compute fabric of some sort next to the network card and next to the actual hard drives. So let's take a step back and look at what a current data center node looks like. So here we have kind of an overview of it, and down the bottom there, you'll see we have Ethernet going in. So this is sort of what we plug into the wall to connect to our network, and that goes into a network interface card. So this is sort of a standard dumb network interface card. There's nothing clever about this one yet. Then we'll have some system memory, some RAM. We'll probably have maybe 100 gig of this or something, and that'll be connected up to a CPU. And we might have some kind of bigger storage elements, such as a solid state drive. Now, the makeup of this might change depending on what type of data center node it is. If it's a compute node, you might have GPUs and things like that. If it's a storage node, you might have more SSDs and system memory. But this is kind of generally, to keep it simple, we have something that looks like this. And in these sorts of systems, the CPU, they're all connected together by a PCIe bus. And in these sorts of systems, the CPU is king or queen. So they're in control of everything, right? So they are responsible for doing most of the computation, or at least saying what should be doing most of the computation. So they kind of control and oversee and manage everything. So they will tell the solid state drive when it needs to get data out and put it into system memory. They will kind of pull packets off the NIC, or at least process them. And this is what's changing. This model where the CPU is the center of the system is starting to change. And part of this is to do that. We're kind of pushing the limits of what we can do with our silicon, and to try and get more and more out of our silicon. We are just pumping more and more complex stuff into our CPUs, and they are consuming more and more power. And this is making our data centers more and more power hungry, and we don't want that. So what we're doing instead is we're trying to make other components smarter and to try and reduce the kind of importance that the CPU has in the system. And the reason for doing this is that we want to perform computation near where the data resides. So on the network cards, we're kind of performing computation as the network packets stream through the network interface card. On the SSDs, we're performing computation as we're reading data out of the SSD or as we're writing data in. So we're doing less data movement is the important thing here, because moving data around is what consumes power. So every time you move a bit, every time you do kind of a read or write to RAM, you are consuming lots of energy, but you're also introducing lots of latency and things like that. So just to kind of illustrate how much data moving goes on, let's think about that standard kind of data center node that I talked about before. And we're going to make it do, so this is kind of a more block diagram view. We're going to make it do kind of a simple task. It will take some data off the network. So some data will arrive as a packet into the NIC, and it will write that data into an SSD. So we've got our SSD there, our NIC there, CPU and system memory. So the first thing that happens, our packet arrives into our NIC with the data that we want to store on our SSD. And the NIC accesses the system memory and writes that data into a buffer. So this actually requires a lot of stuff happening. The NIC has to go out onto that PCIe bus that connects everything together. So these wires that connect up the system. It has to energize those bits going, those wires on the motherboard. It then has to go into the CPU's memory controller, probably has to load some rows into row buffers in DDR or in your RAM or system memory, write those in, and then those get pushed into storage. So there's a lot of kind of movement that happens just in that single thing. Then what it has to do is it has to ring the doorbell, it's called. I always love this term. So the CPU is just sitting there, not really knowing what's going on. We have to tell the CPU that the data's arrived. And so what the NIC does is it rings the doorbell of the CPU. And this basically just interrupts the CPU, and then the CPU can it goes into system memory, then brings that data out closer to where it is, probably in some memory that's close to its processing elements like cache, and it can actually start performing computations on them. So that's more movement again. And all of this introduce kind of variations in latency as well. So, accessing the PCIe bus, if other components are accessing it, then it might kind of introduce delays. And so when you're kind of doing these sorts of movement of data around, you can actually get quite a variation in the amount of time it takes, which is a problem in data centers as well. Now, in our system, we wanted to get data off the network and then write it into the SSD. The SSD is actually even more complicated. We have a buffer that has commands. So the CPU writes a command saying that it wants to write some data into the SSD, into this buffer in system memory. It then rings the doorbell of the SSD. The SSD gets that command, and the CPU writes the data into some other buffer in system memory. In that command, the location of that buffer is sent to the SSD, and it pulls the data in. Don't worry if you didn't follow all of that. There was a lot of kind of parts moving around, but the point I'm trying to make is that there was a lot of data moving around between system memory, between the SSDs, going over all the buses, all of those bits flipping takes a lot of energy and introduces inefficiencies and lots of variation in latency. So with SmartNICs and smart SSDs, we're trying to reduce that movement and that kind of movement of data around the place as much as possible by putting computation close to where the data is. So with a SmartNIC, we will have now a big kind of box that has appeared here, which has FPGA written on it. Don't worry if you don't understand what an FPGA is. I'll explain that in a minute. But basically, it's a kind of very flexible computing kind of device. And we put this right on the NIC. So as packets are streaming in, we can process it the very, very clock cycle it arrives into our system. So instead of having to put it into that system memory buffer, call the CPU fetches it and then performs computation on it, we can do it as it's arriving. Similarly, for the smart SSD, we were doing the same thing. We were putting an FPGA, so this big compute device, or very flexible compute device, right in the package itself. So as we're reading and writing data to and from the SSD, we can actually perform computation as it's streaming out. An example of application of this could be a database. So say you have a big, massive database and you want to filter data between a certain range. So you want to find, let's say, the ages of people between 10 and 11. You could then issue a read to that database, and as the data is streaming out, you could be doing that filtering in the FPGA fabric before it even gets out onto the wire. So not only are you not moving data around as much, but you are also saving the bandwidth of the wires that connect all the components together because less data is getting thrown out onto them. So there's multiple benefits here, right? So, okay, I mentioned an FPGA. This is kind of the way that SmartNICs and smart SSDs are going. So what is an FPGA? So a lot of an FPGA is essentially the Lego of digital circuits. So our processors are made out of AND gates and OR gates and all sorts of digital logic. And an FPGA is essentially a 2D grid of universal logic gates. So these are gates that we can program to be any Boolean function we want for a set number of inputs. And so the reason I say it's kind of like the Lego of digital circuits is that with Lego, you can make any toy you want and you can customize it in any way that you want, but it won't look quite as refined as maybe going to a factory and getting it plastic mold injected and getting the fully polished toy out. But you can change it and you can reconfigure it and you can add things to it however you want, but it won't look as polished. The same is kind of true with FPGAs. You can make any digital circuit you want, but it won't run at quite the same clock frequency as if you went to a foundry and actually got the custom circuit made. So we have this flexible fabric of kind of universal logic gates, and then we have this routing interconnect that we can use to kind of program and connect them up together. And we can change this at runtime or kind of on the fly. We can reprogram it. And so we can configure how these components are connected together, and then we can actually configure the logic gates and we can make processors out of it or custom processors for our application. And so what the next generation data center node is starting to look like is more like this. We have a network connection coming into a SmartNIC that has an FPGA on it that you can build processors on if you want to. And then you have a PCI connection or a direct link connection to a smart SSD where you have your storage. And so what you'll see in this picture is there's no CPU, right? In the previous world, the CPU was king or queen, controlling everything. Now that isn't the case. We have a much more hardware-centric view of the world because CPUs are just not performing as well as they used to be. Now, I'm kind of fibbing a little bit here, and I'm saying that there's no CPU. In reality, the actual FPGAs themselves are getting more complicated. So there's not just this kind of universal fabric anymore of kind of logic gates that you can program. Now we're seeing CPUs dotted in amongst the actual FPGA fabric itself. So we will have like small ARM cores inside our FPGA that we can program and do things with. And these are reasonably powerful. You can run Linux on them and things like that. So we will have some CPU, but it won't be kind of the central component in the system. It'll kind of be off to the side, and you can have it do some functions if you want. So what's the problem? Right, this all sounds great. We're going to reduce the amount of data we're moving around, make greener data centers that can, handle bigger operations and things like that. So the big problem is, and the problem that a lot of cloud providers are facing now, and this is what I found when I worked at Microsoft as well, is that designing custom hardware is very difficult in of itself. So designing an FPGA design is difficult. The languages that you use, and generally if you want good performance, you have to use these languages, are really low level. Think like assembly language, the lowest level that you can use to program a processor, and then go down a few steps. It's a spatial language, so you're just describing a circuit, which is a 2D thing, but in a linear document, which is quite a difficult thing to do. And there's just lots of difficult things that you need to deal with. Also, compilation times are long, so it can take over 24 hours to actually place all the components by the tools and route them all together. It's a very complicated process. So those long design cycles are really quite a challenge to deal with, and the low-level languages. There are higher level approaches that take kind of software languages and map them into hardware circuits, but these don't get the performance that you would want, unfortunately, yet. The next issue is just integrating bits of hardware together is intrinsically difficult. They might have different protocols, they might speak slightly different languages. And when you connect them together, you often find that when a bit of hardware worked in isolation, connecting another bit to it often seems to produce more bugs. Like bugs seem to appear out of just kind of connecting things together. And these bugs can be very challenging to find. If you're lucky, you can simulate the system and actually figure out where the bugs are, but you have to end up scrolling through like waveform after waveform and going a bit cross-eyed doing it. If you're unlucky, it passes simulation, but it fails in hardware, and then you've got nothing. You have no visibility on the system whatsoever. So that's another really kind of tricky challenge that needs to be solved. And finally, the third one is these are all FPGAs that are networked together. Distributed systems are just hard to build in general. And when you try to do all three of these things together, it's nearly impossible. So in order to do this, if we want to make a cloud that is hardware centric, but also available to the public to use, we need better tools and abstractions to actually make it realizable and usable. It's just not going to get off the ground if we don't. So this is where I kind of finally get onto the title of the talk. EPIC is a program grant application that I'm a part of. So we don't have the money yet. We're still trying, fingers crossed, from EPSRC, and it stands for Event-Based Programming Infrastructure and Computing Systems. And we're trying to look at how we can build applications that can realize these sorts of next generation heterogeneous hardware-centric clouds in a scalable way that's actually accessible to users. It's a 7 million program grant from EPSRC, and the academic partners are Southampton, Imperial, Newcastle, and Swansea. And we're starting to get a lot of industry support for doing it. So we've got a lot of support from Microsoft, and they have these FPGA type systems in their cloud, but also from the vendors such as Xilinx, Intel, who are making these devices. Also, Tashi has put me in touch with some people at IBM, and he's been fantastic at getting a support from IBM there. So what we want to do is actually, I'm not going to talk about everything in that grant. I'm just going to focus down on one little bit, which is relevant to this talk, which is this abstraction for how can we make more hardware-centric systems available in a cloud setting. And what we're focusing on is something that we call hardware lambdas. So some of you might be familiar with the idea of software lambdas. So Amazon, AWS have software lambdas, they're called. And basically, it's a function that you can kind of give to Amazon, and they will execute it on their cloud somewhere. You don't really know where or what it's doing, but it's just you give it the function, you give Amazon the function, and they execute it on their cloud somewhere. This allows you to use cloud kind of infrastructure in a very flexible way, in that you don't need to rent a VM, you don't need to set up an environment, you just give them the function and that gets executed on the cloud. And we want to do the same thing, but with hardware. So to actually create hardware Lambdas. So not bits of software that run on a CPU, but custom bits of hardware that are kind of implemented somewhere in an FPGA on some cloud resource. And essentially what hardware Lambdas are is a hardware module, so a block of hardware on the FPGA fabric with a higher order typed interface. So they have like a well-typed standard interface. Now, don't worry if you don't understand the higher order typed interface. Basically what it means is that we can pass functions in as inputs to our hardware blocks. So let me kind of illustrate this with an example. So we've got our reconfigurable sock there. We might have a bunch of hardware Lambdas and a software Lambda. And let's say this bit of hardware is executing and it's got we want to print occasionally or log something to a file. If it's got a higher order function, it means that we can pass another Lambda in as an input, and it could be a software Lambda. So the hardware and software are kind of equal partners in this kind of abstraction relationship. So here we have our hardware module, which I've called foo, and I've passed in this function studded out, and it's going to print, whatever the input is. And this software, this function, it can be kind of passed in at runtime. This doesn't need to be a static thing. Could be a software Lambda on one of the ARM cores. And so at various points through that hardware's execution, it can call this function that was passed in. Control flow will flow into the software Lambda, and it will flow back into the hardware Lambda and execute. And so we can have it logging to a file or doing all sorts of things. And this is kind of huge. Like having hardware be able to do printfs is quite a cool thing. Yeah. And we've actually prototyped this. So during my PhD, we built kind of little prototype systems on a single reconfigurable system on chip. And we were able to get quite fine-grained function calls between software and hardware, where hardware was calling software, not the other way around. And we were able to get 2 million function calls between hardware and software. And so this is sort of representing a paradigm shift in the way that we think about hardware, in that hardware can now call software functions or software Lambdas. And hardware is a network attached equal peer in the system. So it's not some dumb accelerator hanging off a network or off a PCIe bus. And this means that CPUs are no longer the center of the system. They can play kind of a supporting role off to the side. And this makes sense in this world where we have a smart NIC and packets flowing into our smart NIC, right? Because the first thing that those packets see is this custom hardware compute fabric. And so likely our main function will be inside a hardware function as it's flowing through the network. And then if there's some kind of complicated exception or error handling that we need to do, we can then call a software Lambda to handle that. And it doesn't need to be a big CPU doing this. It can be a low power kind of CPU hanging, actually integrated within the FPGA itself. We can also think of kind of processors as containers. So there's, a big move towards containerization where you kind of have programs packaged up in the operating system. We could do the same thing with hardware Lambdas, where we have soft core processors, which are processors implemented on FPGA with a software Lambda inside as kind of one complete package. And you just stamp out a software Lambda kind of hardware component. So it matches this model nicely. So we think that this is an abstraction that fits what kind of the next generation of cloud's trying to do. And the other thing that it does is it separates concerns. Sorry, so I've jumped ahead of it. Never mind. So we have this kind of idea that we'll have multiple FPGAs networked together, and the tool will automatically construct sort of a multi-FPGA heterogeneous Lambda overlay. So you'll kind of give it all the Lambdas that you want in your system, and it will place them out amongst all the FPGAs automatically. And you'll be able to tell it like what can call what, and it will optimize the placement of where they are across the entire system based on that. So we're trying like keep locality and kind of who can call what in mind. The other thing that it will do as well is based on that kind of type system that we've got for linking everything together, it'll automatically generate a language, kind of a specialized language that end users can use, so they don't actually need to know about all this Lambda stuff that's going on underneath the hood. So right, you'll place all these hardware Lambdas will be placed over the system or software Lambdas, and then the network infrastructure and kind of interconnect for it will all be optimized for that. And we can do that because it's an FPGA, so we can actually develop the interconnect however we want. We're not kind of constrained. We're constrained by how the Ethernet cables are connected together, but we're not constrained within the chips as how we actually interconnect these things together. And so then with the automatic kind of little programming language that comes out, a user will be able to come along and use this multi-FPGA overlay kind of at runtime, stitching all these lambdas together, be them hardware or software lambdas. And we also believe that we can make this multi-user. So another user will be able to come along and use a different subset of the lambdas concurrently. So it'll be a multi-user cloud in this giant multi-FPGA hardware software Lambda overlay. And we think that this separates out concerns. So hardware engineers can now focus on making really optimized hardware Lambda cores. And as long as they meet that kind of type system, they'll be able to integrate with the rest of the system. Systems integrators then don't need to worry about kind of what each Lambda is made up of. And the tool will kind of handle the placement and the generation of the language. And application engineers then don't need to worry whether or not they're running on an FPGA or a CPU. They can use that automated language for kind of targeting this multi-FPGA system. And so we're kind of, what we want to do is marry these two worlds that are kind of colliding. So this kind of Lambda approach and build abstractions for doing it with the kind of way that data center infrastructure is going, and make systems that look like this, where you'll have, you know, Ethernet going into a smart NIC, and you'll have hardware and software lambdas that can be configured easily at runtime, and smart SSDs where we can configure stuff as well. Oh, and sorry, that's the end of it. And so we've got this project proposal that we're putting in. The outline's due in July, and yeah, we're excited to see what we can do with it. Thank you very much for listening. Does anyone have any questions?